Welcome to Academic Digest class. So today we are going to be treating or deriving equation of angular momentum. And you need to know first of all, before treating angular momentum, you need to remember that linear momentum is this way, is represented with P. I will say that linear momentum is mass in motion, or you say product of mass and velocity. So for angular momentum is represented with L. This L is simply maybe talking about that perpendicular distance. For everything to rotate, it will be passing through quadrants, which is divided into 90 sections. So we'll just represent it with L. And we'll say that when something is moving linearly, we'll call it mass and velocity. So we'll just represent with mass. But in angular, when a mass can rotate, the measure of the mass in a body and how much it can change or how much it is distributed is called inertia. So we put I for inertia. Then velocity here in angular motion, velocity is represented with W, and we know that these things have its formula. So inertia, in fact, anytime you're thinking about angular whatever, just remember that if something is in angle and it's talking about something, so inertia is talking about mass, so put M and then put R, just that it has square. Then angular velocity is talking about velocity and R. If you remember that our formula, we've derived it before, so all over R. So if you put this together, this can cancel this, so that you get that angular momentum is equals to mvr. That is this. So if you check it very well, you see that everything you have here is looking like linear momentum. So we can say that angular momentum is equals to linear momentum times R. So this thing goes back to that our Mano principle. One could just say, if they ask you what is torque, torque is the force that is found in a body rotating. So that means that torque is equals to Fr. So once you're talking about something in angular, just remember to always put R to it. It's a constant. So now, assuming without even solving all these things I saw, they asked me angular momentum, I could just say linear momentum and R, finish. Okay, let's now progress from Newton's second law. From Newton's second law, we know that force is the rate of change of momentum. Anytime you hear it, know that it's divided by t. So we can say that if that is the case, torque, like I just said, is equals to force and rotating distance or radius, so R. So for when you talk about normal motion, linear motion, we talk about force. When we talk about motion in a circle, the force there is torque. So just say F. So now T will be equals to, replace force here, mv over T. Then your R. So if you check where you see that everything up here is looking like everything you have here. You see it? So which means, yes, which means that, remember, angular momentum is equals to mvr, which is the same thing as saying linear momentum and R. So it's the same thing as say, you can even put this thing this way if it will confuse you. You can say that everything here is equals to L, or you can just say that this thing is equals to P and R. Are you seeing it? All over T. And PR is the same thing as L. So we can say that torque is equals to angular momentum all over time. So you remember that in normal rectilinear motion, force is equals to linear momentum over time, the rate of linear momentum. So you see that they are almost the same thing, force here. So for torque, when it's rotating, this one is the rate of angular momentum. So there you have it. Why I did this thing is that there are so many ways that people do this thing online that is confusing. But if you pay attention, you remember that we always put R once it's talking about angular. It becomes easy. So there are some cases where they now ask you this angular momentum that is PR. If they want to find the magnitude, since the body, this talks about body rotating, it will not have X components. Unless we want to just be arithmetical, like trying to maybe, should I say, I have theta already. Now, when I have theta, I'm not trying to find this side, the angle from theta, then I can use cos. But since I have this, if it's PR, L can also be equals to PR magnitude sine theta. That is when this thing now, when I'm not giving force, and when I'm not giving this linear momentum an r at 90 degrees, it's giving to me, remember vector, at an angle other than that. So I can now resolve it by doing PR sine theta. You notice that this sine means that it's to the y-axis. So torque can also be this. Or you say angular momentum, sorry, I say torque, can also be equals to magnitude of PR sine theta. If it's confusing you, don't worry, when we start solving calculation, you understand better. So that is the relationship between angular momentum and linear momentum, and then relationship between force and and torque. And please remember that for a circle, I said the force found in a circle is called torque, while the force found in linear motion is called F. You understanding this? This one is equals to MA. This one is equals to FR. And you need to remember, you need to also know that the friction found in a circular motion or in a body going through circular motion is called centrifugal force. So it is the force going opposite the centripetal force. Centripetal force wants it to come to the center so that continuity will be there. Centrifugal gives you the effect on your hand. It wants it to stop. So it's opposing it. And centripetal force is any force that acts towards the center, and it comes with a centripetal acceleration. Use notes and be writing what I'm saying down. Thank you. Subscribe.